Okay, so last time we started discussing Riemannian geometry, and today we'll continue doing that. But if all goes well, there's a little calculation we'll be doing today, and if that goes quickly enough, then we can actually start talking about the relevance of all this to general relativity. And it's certainly true that in this course I'm introducing the main subject of the course, which is general relativity, when we are already we are pretty far down the course already. And that's because this is an extraordinary subject. But I have introduced two things, and both of them are ingredients in general relativity, which without them you will never be able to understand it, which is special relativity and unlike the textbooks that you have probably followed in first and second year, I've used the language of Minkowski spacetime, which actually simplifies the mathematics a lot. I've also introduced Riemannian geometry. And this is simply the geometry of manifolds with a metric. So, spatial manifolds with a metric that can be expressed in different coordinate systems, and the metric is written Gij of x. Now, Minkowski spacetime is four-dimensional. It has x, y, z, and t. But the Riemannian manifolds we discussed are three-dimensional. They only have x, y, and z. So these two don't have these two discussions have no overlap. Okay, this concerns space, which is more general than flat space. This concerns ordinary space, but augmented with time and with some symmetry under change of frames of reference from one frame to another, keeping the laws of physics invariant. Here we can't use language like change of frame. We can only say change of coordinates. In a Riemannian manifold, you just change coordinates, okay? Or you change coordinate patches. You on some overlap, you go to some new coordinates. Here also you change coordinates, but the physical meaning is change of frame, if that change of coordinates involves time. If it doesn't involve time, of course, it's still just a change of coordinates, okay? But here we actually talked about changing space-time frame. In general relativity, both ideas will come together, but for now we have been discussing them separately. Here, the purpose of the discussion was to understand the physics of space-time in the simplest space-time. Here, the purpose is to understand the mathematics of manifolds, just that. Later, we have to understand the physics and the mathematics of space-time manifolds, so everything gets combined. We are going to continue with Riemannian geometry now and derive an extremely important formula which probably influenced Einstein to think about his theory. So what we want to do now is to take a generic Riemannian manifold with a metric that we don't know. It could be anything subject to the requirement of being smooth and positive. In Riemannian manifolds, the metric has to be positive. That means any 2 points which are not the same have to be separated by a positive distance, and the distance is calculated by the distance element Gij, dxi, dxj, square root. And this quantity is invariant under all changes of coordinates on the manifold, because x obviously transforms under that change and g transforms in a compensating way to keep this whole thing invariant. All this we know. Now today we are going to ask the question, how do we, what path extremizes the distance on a Riemannian manifold. So purely geometric question. An old version of this question was asked by mariners who steered ships. They don't want to take a longer time to get from A to B than necessary. So obviously on the surface of the earth, they have to answer exactly this question. What path extremizes, actually minimizes the distance, so that if they follow that path, they'll reach the other end fastest. Today, airlines also do the same thing. They have, of course, there could be political considerations and safety considerations, but if we ignore them, then airline has a job of getting from departure airport to arrival airport, following the shortest route to burn the least fuel. So it's a very important kind of question. So that is exactly the same as extremizing this function over paths. So it's an extremizing problem. Okay. Now it's a very simple calculation and more or less equivalent to what I'm going to do to extremize this function and find out what equation is satisfied by the path. But there's a very cute trick, which is that I can convert this to a physics problem. Just an auxiliary physics problem, not a general relativity problem. And the analog physics problem what is the equation of motion of a particle constrained to move on a Riemannian manifold. So yeah, just on a Riemannian manifold. We can just ask this question as a question in classical mechanics. And actually, I'm always surprised that it's never asked as a question in classical mechanics. It's such a simple and beautiful question. And what it does, it generalizes the study of free particle in an interesting way. So normally we take free particle, half mx dot squared or half mv squared is the Lagrangian. Then we add minus v of x. But here we are not putting any potential. Instead, we are complicating the space. That's also an interesting thing. And putting a potential is a way to complicate the theory, but changing the space without putting a potential is also a way to complicate the theory. So we have the usual Lagrangian half m xi dot squared in flat space, in Euclidean space. I don't like this word flat because I haven't explained it. This one, I is summed over from 1 to 3. This is the Lagrangian of the free particle, is the kinetic energy term. And when I extremize it, I get x double dot I equals 0 as the Euler-Lagrange equation of motion. Straightforward. Now, I'll change my Lagrangian to reflect the fact that the particle is moving not on Euclidean space, but on a Riemannian manifold. Then I'll calculate the Euler-Lagrange equation of motion, and whatever I get will automatically be the solution to my problem. It will be the generalized equation of motion in the presence of a non-trivial Riemannian manifold. Okay. So the only thing that we have to guess is what should the Lagrangian be. So for a manifold which comes with Gij of x, what should be the Lagrangian? Any guesses? Of course, it should reduce to that exactly when Gij is delta ij, identity. Yeah. So then, very good, everyone's got it. I can just use the dot notation. That's it. Notice that because Gij depends on x, the metric depends on where we are on the manifold. So this is no longer quadratic in x. That one is quadratic in x. This is nonlinear. The same thing happens if I take this one and I add v of x. V of x typically can be some potential like sine or something. It need not be quadratic, could be 1 by x and so on. So that's what makes the mechanics problem interesting, and here we have made it interesting by a completely different method, by simply putting a metric. We could also have added a potential, but we want to know what a particle is doing when it's constrained on a manifold with no potential. Now here, since this is a physical system, I want you to think very carefully. When I say constrained on a manifold, and otherwise free, I don't actually mean that the particle lives on, say, a sphere or some manifold that I make in my lab, for the reason that the force of gravity will act on it. So it's not free. I'm studying something which has no force acting on it, but for the fact that it's constrained on the manifold. And if you want to think a little carefully about this, you might say, well, if I have, let me take some weird kind of shape like this, and it's a two-dimensional shape. I make it out of some plastic or rubber or metal or something, and I put my particle here. The particle, of course, because our space is three-dimensional, has the option to propagate at any point in two linearly independent directions along this surface, and its third possible direction is out of the surface. When I say constrained, I mean that out of the surface direction is somehow banned by some means. You can think of it as like imposing some infinite amount of force which keeps it on the surface, but once it's on the surface, it experiences no force. There's a famous mathematics problem, mechanics problem of a bead moving on a wire. That's an example. The bead is only free to move on the wire. It's not free to leave the wire. But while it's on the wire, you're not supposed to imagine any force acting on it. You can imagine a freely moving bead on a wire. If you really have to do this experiment, first you figure out how to anchor the particle onto this surface, and then you send this whole thing into outer space where it's weightless, and then you have actually that problem. But that's only if you want to actually do it. We are free to think about it without doing all that. I hope it's clear what I therefore mean by a particle moving on a manifold. Yes?
So I'm a little bit confused. So if you think about a bead on a wire,
yeah,
we can think of it as a free particle in 2D Euclidean space, but the potential is such that it goes to
it's actually so it's actually not free in 2D Euclidean space because of the constraining force on the wire, but it's free in 1D space. The wire doesn't have to be circular, it can be any wire. As long as the bead is stuck on the wire, it has one direction of motion, and it's free in that direction. But there's nothing pulling it or pushing it. And again, in your mind, you will think of a roller coaster, and that when it comes down, it goes fast, and when it goes up, it goes slow. That's not what happens, because we are not even including any external force like gravity. It's just free. Okay. Now, there's nothing very interesting in the case of a wire, because it so happens, for a free particle, it so happens that I can just by a coordinate transformation map the wire to a straight line, and I get a free particle on a straight line. And what can it do? It can go left or it can go right, and there's nothing interesting. This coupled with the fact, or related to the fact, that there's no Riemannian geometry in one dimension. All Riemannian geometry in one dimension is trivial by change of coordinates. It starts being non-trivial from 2 dimensions. So you have to imagine this situation on a non-trivial geometry, particle anchored on it. Instead of saying we need a force to anchor it, we just idealize that it is anchored on it. It has no force, but it can't. That option of leaving is not there, and the option of moving in any direction here is all. There's no force, so it's not prevented from doing anything. Okay, and that thinking naturally leads to this Lagrangian. And now all we need to do is find its equation of motion. Okay. Now, just not to make any mistake. Good. So, equation of motion is always this. So what is del L by del x dot k for this Lagrangian? X dots are here and here. If I differentiate this one with respect to k, I get delta ik. So this I will turn into a k. So I get gkj x dot j. The reason I didn't put a half, sorry, this I'm putting a mass here, though it won't play any, as you can see, it's not going to play any role in the equation of motion because it's an overall constant. It's just that I want it to reduce to that. So if I differentiate in this x dot, I get half m gij times that x dot. If I do the other way, that x dot, I get the same thing by relabeling of indices. So the half goes away and this is the answer. What about del L by del xk? Now here, the only thing that depends on x, so when we differentiate in x, then x dot is treated as constant. When we differentiate in x dot, then x is treated as constant. This is how partial differentiation is done. So when we differentiate in x, these things don't care, and we differentiate only here. So how do we do that? So we write half m. Now that gij is differentiated in xk, and there's a very nice notation that expresses it. This is nothing but del by del xk of gij. When I differentiate in xk, I basically add one more index to the thing. So it has these two indices down, and this also is down because it's up in the denominator. We've discussed that before. So I can write it like this. So the comma simply means differentiated with respect to xk. So that's simple. Okay. But now that's not enough. Now I need to differentiate this guy with respect to t. So let's do that. So from this we get, so now when I differentiate with respect to t, where is the t dependence in this? It's in x. X is a function of t. So I have to differentiate this, and I also have to differentiate this by chain rule with respect to x, and then x with respect to t. So I actually have two terms. So d by dt of del L by del x dot k is equal to m g k j m x dot j plus m g k j x double dot j. So in this term I differentiated this x. In this term I differentiated g with respect to xm, and then I differentiated xm in time. So two terms. By the way, when you do all these calculations, you can always make yourself feel better by asking what would be the special case if gij was just a constant, which you already supposed to know. And the answer is all the terms where gij, comma, anything is there, those all go to 0. And so in the end, you will see that this is actually this double dot term is the only term that survives, and you will get x double dot equals 0, mx double dot equals 0, which is Newton's law for force-free motion. So we are just generalizing that law by changing the manifold. Okay, now I have to combine everything. So the claim is that this, therefore, so Euler-Lagrange says that now I can cancel m everywhere as I expected. So I get gkj x double dot j plus gkj m x dot j minus gij k x dot j equals 0. There's a half which I've lost somewhere, I think here. This term had a half. Good. So one thing always to check your equations, is the free index the same in all the terms? The index here is k, j is contracted. Here it's k, j and m are contracted. Here it is k because I and j are contracted. I hope now by now you're slowly getting familiar with the idea that the indices which are summed over doesn't really matter what we call them. We just have to call them something, but they are summed over. I can rename them and it will still be the same thing. Good. So this is our equation. Again, if we stare at it, remember G is invertible. So we can invert this G and multiply it into the rest of the equation, and we'll get x double dot plus some terms which are of the form x dot squared is equal to 0. I want to emphasize here, it's always important to think what the equation is telling you at every step. It's like a loop. We do algebra, then we think, then we do algebra, then we think. There's also a bigger loop. We do algebra, we do geometry, then we think. But if you do any one of these, if you only do algebra without thinking or only thinking without algebra, result is going to be very bad. You're just going to get yourself confused. So I want to emphasize the importance of thinking. Just inspecting this, you can say something without knowing any details. This is acceleration of your particle. This is velocity of your particle. The curvature has created a velocity dependent force. Great. Just a fact. It's true. Okay. And if this was 0, velocity dependent force would go away and you would have your ordinary no force. So there is something like a velocity dependent term. It's not really a force in the sense it's a free particle. This is because we are using different language. The free particle is, so Newton's law does not say F is equal to ma on a curved manifold. It says F is equal to all this. M times all this. So I wouldn't like to call it force. I'll just say it's a velocity dependent term which contributes to the response of a particle to a force. But here we are force free. So let's invert this, this thing. So I have to multiply from the left by some G with upper indices, and I'll multiply by GKL. So GKL, when multiplied into this, K will get summed. This is the inverse matrix of this. So I'll get delta Lj, and this will become x double dot of L.
Excuse me.
Yes.
While interpreting the equation, so you says that when a force is applied on the object,
Yes.
it kind of have something to do with velocity. But if we were in the Euclidean space, there is no such velocity term.
Yes,
as-
yes. But actually this velocity, so the reason for the velocity is the curvature. Okay, so what it says is that the equation of a free particle on a curved manifold involves not just the acceleration but also its velocity. And we are going to write that equation very soon. This is the equation, we are going to just write it better. Yes.
So here you're multiplying with GKL, right?
Yes.
I feel like I could be wrong, but shouldn't it be something like GLK multiplied?
G is symmetric. Absolutely no difference.
Ah,
Once we know that G is symmetric, you're right actually, if I want to be very pedantic, it should be GLK. But one thing we do in this subject is that when it's symmetric, we write the indices how we please. We just don't care. As long as we are sure that it's symmetric.
So it can't,
But, huh?
can't we use this as the external force which is constraining it to the...
No, this is, you can't, because see, this thing, when there's a force, this will be some finite number, finite thing. But constraining force has to be infinite. It has to be, this is a equation only in the lower dimension. This is, for example, on a sphere, K and J only take the values 1 and 2. Now you may ask, what are those coordinates called? Well, we don't know because we don't know this manifold. It's some arbitrary manifold. I can call the coordinates anything I like. On the sphere, it might have been the Euler angles theta and phi. Okay, so J and K would then take the values theta and phi. So if you want to apply this to the sphere, you have to find the sphere metric, which was a question in your quiz, and you have to say K equals 1 is theta, K equals 2 is phi, and then write this equation, which is a set of equations for all the values of K, a pair of coupled equations. One of them will be when K is theta, one will be when K is phi, and you write them, and now it's your problem to solve them. This is exactly how you would solve for particle motion on a sphere. Yes.
So I just had this thought. G is symmetric because distance between A and B is same.
G is symmetric because it's the metric tensor, and the metric tensor is by definition a symmetric tensor.
It has nothing.
Yeah, it is because its only appearance is in the form of Gij, dxi, dxj, and dxi, dxj is symmetric because they are both the same thing. So another way of saying it is, if it wasn't symmetric, the non-symmetric part wouldn't contribute to anything. You can see it from our original Lagrangian. If G was not symmetric, the rest of it would have dropped out.
Basically, we can always symmetrize it. That's
So it is taken to be symmetric. The metric is always defined to be symmetric. But good question. Good. Okay. Now we'll do this. We'll contract K with K here, K with K there, K with K there, and we'll rename indices. And now you probably won't very quickly be able to agree with the next equation. You will see that it has the right form, but to understand all the index placement, you actually have to do it yourself. So this is one of the main lessons of this subject, and if you signed on to this course hoping you won't have to manipulate indices, then I'm sorry, you're in for a lot of disappointments for several weeks to come. Okay. So the equation, as I worked it out, I think it's correct, is this. Now there's a little extra trick I did which I'll just explain. So this is my Euler-Lagrange equation. Certainly you'll agree that after I multiply, okay, I could call this, yeah, I call this L because there's already an I. It's very dangerous to use the same index again if it's already in the equation. But after I'm finished, I can rename I as something else and L as I, just to suit me. Just make sure you don't have 3 or more indices which are the same in any equation. If you have 2 which are the same, they are summed over. You can always rename them to something else and you'll get this form. And now there's only one little trick. You can see it roughly looks like that because x double dot comes here with that g having removed this factor. Here you get g inverse g comma something and minus half g inverse g comma something, and the whole thing multiplies the 2 velocities. But instead I have 3 terms. So what I did was to take this single term and write it as half times the sum of 2 terms. Why am I able to do that? You see, this is g kj comma m, x dot m, x dot j, but I could also have written it g k m comma j because it's multiplying something symmetric in m and j. So I simply take half each way of writing it. I've not changed anything. And that's how I got these 2 terms to both have half, and the last term also has half, and this is the equation. Yes?
So you are assuming that your differentiation is also symmetric?
No, I'm not assuming. Where am I assuming different? See, differentiation is symmetric only, that comes in only if I take 2 derivatives. No, I've only taken 1 derivative. Actually, it turns out very important that I've only taken 1 derivative. Tomorrow we'll take 2 derivatives. It's a very slow process. We've just taken 1 derivative, so we don't have to assume anything about that. These are summed over indices. And because of that, I could just rename m as j and j as m, and then this would just become m comma j. Okay, so this is the form. Again, if you were following from the beginning, then this is the x double dot term, the acceleration term, so to say, and this is the velocity squared term. So that's always been there. It's only a matter of checking that everything is exactly, all the indices are placed exactly right. There are many things to check. For example, now this whole expression is symmetric in j and k. Why? Under exchange of j and k, this goes to that, that goes to that, this goes to itself because g is symmetric to start with. Okay, so it's very good. And now we simply give a name to this whole thing. Capital gamma I j k is defined to be half g I L g j l comma k plus g k l comma j minus g j k comma x, just this stuff. So it's a three index object with one of them being up and two down, made out of metric and its inverse and its first derivatives. No more derivatives than that. Okay? And this has a name, it's called the Christoffel symbol. After the person who first wrote it down for geometry. And with this Christoffel symbol, we can simplify our equation x double dot I plus gamma I j k. Remember, it's a function of x dot j, x dot k equals 0. And so we have got a nice equation for a free particle moving on a Riemannian manifold. It's amazingly simple. It's different from the Newton's one, which would have been x double dot equals 0. We can see why the difference is there. It's there because G is not only not identity, but it's in fact space dependent. Therefore, it has derivatives. Okay. Now, let me give you one very funny example which will make you understand the importance of this. Supposing somebody gave you the metric ds squared is equal to dx squared plus x squared dy squared. Is this something you can recognize? Is it anything you know? Would you know what to do with it? It's a metric. It certainly satisfies the properties of a metric. Anything you've seen before? Okay. Yeah, I don't want to mock you, but I want to tell you a story of my nephew when he was in 6th standard, 6th standard. He said, you know, they taught us in school that x plus y squared is equal to x squared plus 2xy plus y squared. I don't know if it was 6th or 7th standard. And then he says, now in the exam they asked us what is a plus b squared, and he says, you know, my friends didn't know the answer. This is a very smart nephew. He said, but you see, it's just a matter of the name. It's the same answer with the names changed. That's very abstract for a 6th standard student, but it should not be abstract for you. I hope you agree. Okay. So now let me write this same metric as dr squared plus r squared d theta squared. Does it look any better? Exactly the same metric. It illustrates a very deep point actually. When you see a metric, you don't have any idea a priori whether the coordinate is an angle or a length, whether it should be positive, allowed to be negative, whether it's compact. So once you see this, you say, oh, r goes only from 0 to infinity and theta only goes from 0 to 2 pi. Unlike what our mind would say that x and y should go from minus to plus infinity. Not so, right? But you have to deduce that from the geometry which you deduce from this metric. It's a hard problem and you will encounter this repeatedly in general relativity. You'll get a metric by solving Einstein's equations. It's up to you to figure out what the coordinates mean. They don't come with any instructions. And what we do there is to simply make them valid on the largest possible region of that they can be valid in without spoiling anything. And then we say that's a coordinate patch for this metric. And coordinate patches are not unique. Somebody who is very conservative might say, I'm going to allow r only to go from 0 to 1. Now it will be the metric of a unit disk. Okay. Somebody else may say, I only want to allow theta to go from 0 to pi. Then it will be a metric of a half space. And then somebody will say, look, let's try to make it the biggest space we can make with these coordinates. And then you will realize that it's the full Euclidean plane minus the famous point at the origin. And then you say it's 1 point, no problem between friends. We'll just take limits when we go near that point. Or we'll use another system when we are near that point. So this is how coordinates work. So why did I bring up this? I've forgotten. Yeah, good. So now supposing I had the original way I wrote it, dx squared plus x squared dy squared, and I asked you what is the shortest path from a point xy to a different point, let's say x prime, y prime. Now when you look at a graph like this, you'll say shortest path, straight line. Okay. Now, supposing I relabel these points for you as r theta, oh, sorry, yeah, exactly. Now I relabel the points for you as r theta and r prime theta prime, and I choose r to be the same as r prime. So it's just r, and this is theta, this is theta prime. So these are these 2 points. Now if you weren't thinking, you might say, okay, the line, the shortest line between these 2 points is the one where r remains fixed and theta varies from theta to theta prime. That's this line. Is it the shortest line between those 2 points? No. But if the metric in r and theta was dr squared plus d theta squared, then you would simply say that the shortest line is the line of constant r where theta varies. It's because of this extra feature in the metric that this isn't the shortest line and that's the shortest line. So this is why it's important. So you have to solve this equation to find out the straight line in polar coordinates. I'll give that as an exercise. The straight line in polar coordinates is not obtained by just saying x double dot equals 0, because it would say r double dot equals 0 and theta double dot equals 0. And then you would realize that to go from this to this, I should just vary theta without varying r, and I would get the wrong line, not the shortest line. That's not the shortest, this is the shortest line. So this is just a simple example to show you the importance of that equation. Now historically, people who wanted to know about shortest lines on planes and spheres and using polar coordinates didn't have to bother with all this. There are simpler ways of doing it. On the plane, the simpler way is to go away from polar coordinates back to Cartesian coordinates, where everything is simple. The metric has no coefficients like that, and then these terms are not there, and Newton's law is true in its simplest form. But you can't always do that in a general manifold. You can't even do that on a sphere. Good. Okay. Now this has a name. It's called the geodesic equation, and it has a very central role both in Riemannian geometry and in its generalization, general relativity. And the statement is a free particle on a Riemannian manifold will follow the geodesic equation, will travel along geodesics. So that's the geodesic equation. Any solution of it will be called a geodesic. And that solution is guaranteed to extremize the distance between the 2 points. There are cases, slightly weird cases, where it might actually maximize the distance also. So one has to be a little careful. But at least if the points are not too far apart, it will generally minimize the distance. If you imagine a manifold which is extremely bumpy, it's not even clear, which one will maximize or minimize. There may be some thing that it goes round, some handle-like thing in the manifold which it goes round, and also it's not that simple. But locally, it's always going to act to minimize the distance between nearby points. Yes.
Just to clarify, it follows a geodesic because it is a free particle.
Yes.
Potentially
Yes.
it
Yes, because we got it by finding the equation of motion for a Lagrangian for a free particle on a Riemannian manifold. And everybody agreed with that Lagrangian. Interestingly, the Lagrangian doesn't depend on, it depends on the metric, but doesn't have any mention of derivatives of the metric. But to get the equation of motion, we need to differentiate the Lagrangian, right? Because Euler-Lagrange equations are differential equations in terms of the Lagrangian. When we do that, we end up with these derivatives of the metric. But cleverly, we package them into a single quantity called the Christoffel symbol, and now it looks quite simple. And of course, again, I'm sure it's obvious, supposing I had 3 different coordinates I equals 1, 2, 3, the acceleration of x1 will involve all possible x dots, 1 and 2, 1 and 1, 1 and 3, 2 and 3, 2 and 2, 3 and 3. because as long as all components of this are non-zero, which we don't know in advance. So the velocity in that direction could influence the acceleration in that direction. It's very complicated. But it should be complicated because we are talking of the most general geometry. What you realize now is that physics is simple when we work in Euclidean space. It's not simple if we and in Cartesian coordinates. It's just not simple if we work in any other space or any other coordinates. Yes.
One more small. We assume that GIG only depends on the position of the particle. It doesn't depend on any velocity.
No, good. Gij does not depend on velocity of the particle. See, the point is that Gij was never defined for particles moving in time. It's defined as a property of an abstract space called a manifold. There's nothing like time. Okay, we adapted it to write a Lagrangian. In the Lagrangian, we said that as a particle moves, we anticipate that the Lagrangian will involve Gij of x of t. So its actual motion will tell me where it is, and that wherever it is, the Gij of that point is appearing in the Lagrangian. So Gij all along that trajectory is relevant for this motion.
So,
Yes.
can we always mimic the effect of the potential by taking it to a manifold?
No. Good question. Can we mimic the effect of a potential by taking it to a manifold? No. And that's a very nice thing. A potential creates a different kind of, actually creates a force by gradient of the potential. The manifold actually doesn't create a force. This is force-free motion. We are interpreting it with language of velocity and all, but it's only curvature. It's motion due to curvature, free motion due to curvature.
But I'm thinking like the effect of the potential, like I mean, can there be a kind of analogy like we can so to mimic the effect of the potential, let's say we take a manifold, and in the manifold when we treat the particle with no force there, and that corresponds to the
Good. So let me ask you, are you thinking of a potential that depends on only x, or can it be velocity dependent?
only depends upon x.
That you can't do. What you can do, I'll show you. You can do the following. You can say L is half Gij x dot I x dot j, and I'll write this as half x dot I squared with an m plus half m by 2 Gij minus delta ij, this is of x dot I x dot j. You agree with this? I've just rewritten this as a fake flat space term, and then I subtracted the same term here. So I can call this whole thing a velocity dependent potential. So it can be mimicked by a velocity dependent potential.
But not for position.
But not not an only position dependent potential. And you can see the reason why. At any instant where x dot is 0, this doesn't experience acceleration at that instant. But with the potential, even if x dot is 0, it will experience some force. Yes.
How can we say or show that the path of the point will be locally minimized and not be maximized?
Yeah. I think that, okay, that's a little more complicated discussion. Let's have it later on. But it seems to, basically the idea is that if I make a distance stationary over a small region, what is the possibility that it could be maximized is that I'd find a solution which goes from here, travels to the moon and back, and then reaches the other point. Okay, and it's very unlikely, unless there's something very special in that manifold, that that one will maximize. Okay, but the whole maximization and minimization issue is quite subtle. But I think let's just take it that as long as it's stationary, we get this equation, and this equation you can integrate. When you integrate, you can see for yourself that it's actually just trying to get to the other place, the straightest way it knows. Yeah.
So is there a uniqueness theorem for the solution to this equation? Because
The
if I
same,
have
okay.
different solutions,
Well, it's the same answer as for any other second order differential equation in one variable. The answer is, if I give you the initial x and x dot, then there's a unique solution. It's exactly like for x double dot I equals 0. There's not a unique solution. Solution is x equals x0 plus vt. So there are two initial conditions, the initial position and the initial velocity. You can fix both over here and you'll get a unique solution.
potential
Hmm.
argument.
Hmm.
So you were saying that if it's a, is it only potential, like only velocity dependent potential can be mimicked, or a
Yeah.
velocity plus space dependent?
Yeah, velocity and space, because you can see this potential depends on velocity and
And
also
space.
through space.
Okay.
Yeah, yeah, position and velocity. Velocity dependent potential is a general term used for any potential which, in addition to space or position, also depends on velocity. Now, why don't we do this? Because we would completely lose the geometric intuition behind the whole calculation. Okay, it turns out once I know gamma ijk is going to appear in every formula that I derive on a Riemannian manifold. But if I work in this way, I'll have to keep deriving everything by doing partial differential equations. So this is not a useful way to do it. It's just conceptually here.
I also have another doubt regarding the equation of motion we find out. So
Yeah.
the assumption basically we have taken, or the Euler-Lagrangian equation we are
Hmm.
following, is the one where the path is extremized.
Yes.
So that itself answers that it is locally extremized.
Extremized, but with extremal could be a minimum or a maximum.
Maximum.
That is the maximum is the problem. In our mind, it should be minimum, right? A free particle going from, well, you could ask the same question for x double dot equals 0. In particular, that just extremizes the kinetic energy, but does it have a solution where the particle starts here, travels to the moon and comes back? No, it just moves in a straight line. But on non-trivial manifolds, that question can be a bit weird. Let me give you an example, since you asked. Supposing my manifold is this thing, donut or bicycle tube or whatever. It's called a torus. I'm sure you know that. Now, from here to here, I can go this way, and I'll get some solution of this equation if I know the metric. But I can also do this. I can go here, go behind, come out, and then go here. That's also a path. Now, which of these paths will extremize the distance traveled from here to here? Answer is both. Because this path, supposing it went behind and came out in here, now I put a rubber band on this and I stretch it as tight as possible. So I will get a minimum. Okay, it will extremize in both paths are minimum length, but because of the difference between minimum and local minimum and absolute minimum. The absolute minimum between this one and the straight path is the straight path, but this is a local minimum because in fact it's topologically it's an absolute minimum in a different topological sector which winds around that thing. You can't deform that one to the original one because it has gone round. And remember, you can't pull it through the torus because surface of the torus is my manifold. So I'm just saying the whole discussion on minima and how many and whether they minimize or maximize, all those discussions are super complicated. But if we'll be satisfied. So in fact, in a way, to answer his earlier question, there isn't a unique path from here to here that minimizes the length. There are many extremal paths because of topology. So let's not now go to the extreme case. Let's just be happy with this equation. We have to solve. We haven't even solved it yet in any example. Yeah. Yes.
Yeah, I was going to say you could have winded it like 3 times.
Yes. And they are all different sectors, as they are called, topological sectors. And all of them, in all of those sectors, there will be one which has the minimum length. But it will be much more than the direct length. Okay. Now we have to face a very important puzzle, and that puzzle comes to us exactly because we are understanding that this is a geometry problem. The puzzle is this equation true after I change coordinates? After all, the whole point of geometry is that things should not depend on my choice of coordinates, and the metric we know transforms as a tensor that guarantees that the equation, the invariant length gij dxi dxj is the same in all coordinate systems. Okay, but here, first of all, we don't know much about this gamma ijk. Is it a tensor? Turns out it's actually not a tensor. And also, it turns out we can calculate whatever it does under change of coordinates because we know what g does. Secondly, it turns out this isn't a tensor either, x double dot. It's a tensor meaning rank 1. These all have, so this has rank 1, so it's a vector. x is a vector, x dot is a vector, x is not even a vector, x is a coordinate. X dot is a vector, that's the velocity vector. X double dot turns out is not a vector, and we can show that. And so it's very non-trivial. The fact that the whole equation is invariant under change of coordinates comes about because this transforms in some slightly strange way. This also transforms in some slightly strange way, and the strange terms cancel between both of them so that the equation is invariant. It's a tedious calculation, and I'll try to sketch it for you now and then leave it to you to work out. However, you could have predicted it. You could say, well, this is the equation from a Lagrangian which is invariant under change of coordinates. So how can the equation not be invariant under change of coordinates? Very valid point. But actually showing that this is not invariant, that this is invariant under change of coordinates requires quite a lot of work, and that work will come in useful later. So we have to do it. So for this, we simply do a tedious calculation and calculate the change of this Christoffel symbol under a change of coordinates. And what we find, so let me say xi is equal to a function of some new coordinates x prime. So what can I say about gamma I j k of x in terms of quantities depending on x prime? Well, this is the answer. Let me write it out, just copy it out. Now this term, if it was the whole answer, which it's not, would actually be correctly a tensor. Third rank tensor with one contravariant and two covariant indices. These two terms act on these indices, this term acts on that index, and the rules I've already told you. So it's very straightforward, but there's a new term. And I can also show you where it comes from. And this new term doesn't depend on the original gamma, or doesn't depend on this gamma. So you see that even if gamma prime was 0, by a change of coordinates I can get a gamma which is not 0. Now why is this a good thing? It's for a reason I explained to you 10 minutes ago. In Cartesian coordinates gamma is surely 0. But I already told you that in polar coordinates it's not 0. And that's good. It's not 0, and that's why we get the correct geodesics on the plane in polar coordinates. If it was 0, we would get wrong geodesics. Okay? This equation is consistent with that fact because a 0 gamma in one frame can lead to a non-zero gamma in the other frame under this under a generic change of coordinates. It's actually a good thing. But it means gamma is not a tensor. Because a tensor is not supposed to have this term, and very importantly, if a tensor is identically 0 in one frame, it's 0 in all frames. I didn't emphasize that earlier, but it's true. That is exactly why we are trying to write equations of physics which always are of the form something equals 0, and then we want them to be frame independent. So if we write them as tensors, we are done. If they are 0, then they remain 0, but not this alone cannot appear in any equation of physics unless its presence is compensated by something else. Now it's very easy to also see why x double dot is not a tensor. So xi prime is xi prime of x. So this is called the rule of transformation of a coordinate, which is just the general invertible coordinate transformation. It can be highly nonlinear and anything. That's what we've always done for a Riemannian manifold. Now, if we take, supposing this was a function of some parameter t, I won't write it here, then x dot I, so this is this. So x dot I is equal to del x prime I by del xj x dot j. This is the proof that this thing is transforming as a vector. This is exactly the rule for transformation of a what kind of vector? contravariant. Now let's do one more derivative. So I d by dt on this side. So I get this. But I also get del 2 x prime I, del xj, del xk, x dot k, j. Because d by dt on this equation will differentiate this prefactor. To differentiate this prefactor, I need to take its second derivative in x and then differentiate that x with respect to time. So I get this new term. So therefore, we've proved that x double dot is also not a vector, just like gamma x dot is also not a vector. But you see that the fault is somehow the same on both sides. There's a similar second derivative problem. And so it is hopeful that the two terms in the geodesic equation will cancel, and that's your exercise. Okay, it's done, it's worked out in detail in the notes, which I will share later today. So conclusion, also out of time. The geodesic equation is invariant under a general coordinate transformation or general change of coordinates, but each of the terms separately does not transform like a tensor. And why not? Because there is an inhomogeneous term. Let me explain that and then I'll stop. So as a vector in this case, due to inhomogeneous terms. Inhomogeneous term is one which is not proportional by some combination to the original one. This is of course a function, so it's not this. This is not the same, not just a constant linear combination of this, but it's certainly proportional to this. It's a non-constant space-varying linear combination of this. But this is the inhomogeneous term. And what you see is that a change of coordinates can create it when it wasn't there before. Okay, so in a coordinate system, you might have a particle which has no x double dot, and after a change of coordinates in the new coordinates, it has an x double dot. Okay, and the problem is if we use words like acceleration, for that x double dot we get confused. But the example of polar coordinates I showed you tells me exactly that, because a particle which in Cartesian coordinates has no x double dot, is just moving peacefully in a straight line, in polar coordinates is doing something unnatural. It's not moving at constant r, it's moving in a way that r and theta vary so that it's a straight line. The straight line in general in polar coordinates is an unnatural thing in their coordinates, but it arises because of this inhomogeneous term. So one exercise you can do is to understand the motion of particles on a plane, but not starting from the origin. Take a particle that starts anywhere and goes somewhere else. We use polar coordinates in physics because we have always got some spherically or circularly symmetric problem. But if you don't apply it to that problem, then you realize these difficulties. Okay. But the good thing is that the geodesic equation is nevertheless invariant. So the fact that the particle extremizes distance, that does not depend on the change of coordinates. Very, very important. And tomorrow what we'll see is when we reinterpret some of these geometric concepts in general relativity, which I'll introduce tomorrow, you'll see that there are even physical ways to understand all these strange properties. Okay, what you'll see, well, let's not say anything more. Okay, so tomorrow.